Okay, good afternoon. We will continue our studies of asynchronous circuits. Asynchronous is still important because you see it's examinable. We still have a question in your final paper. Which deals with asynchronous circuits. Okay, so the key difference is this, and we won't have a very long lecture because I believe on Wednesday we will be having our short test. Is that correct? Yes. We'll be having a short test on Wednesday, and that will cover everything including today's lecture. Thursday will be a final lecture. We'll have a general outlook of the whole course. I'll show you, I'll give you the circuit of how to build a digital clock. When I say clock, I mean, you know, like your clock, digital clock or alarm system, and we'll share some other experiences. Okay, now the main point was this, guys, that in synchronous circuits, all the clock lines were all tied together. Therefore, it was clock. Now, the key point, another key point is when you look at a flip-flop. Okay, I want to discuss with you some flip-flop basics. You may have seen this in the notes earlier. Yeah. I see. I see. I see. I see. I just want to show you with clear. Okay, that's a good picture. There we go. Okay, this is our JK flip-flop. Now, let's kick off our today's discussion. You see, on every flip-flop, up till now, we've been using, and this could be the T flip-flop, this could be the SR flip-flop, or it could be the D flip-flop. Okay, so this is the JK. It could be any one of those four flip-flops. Now, if you look at it, like what we've been doing in our project and all these things so far, we've been using the J line, the K line, we've been using the clock, the Q, and the Q bar. But if you look at it properly, there's two more over there. Something known as clear bar and preset bar. Now, what do these two lines do? Now, clear bar, now the fact that it shows a bar on top, can you see there's a bubble? Both of them, there's a bubble, right? From the clear line, there's a bubble, which means you need a 0 to activate that line. And same thing goes for the preset. You need a 1 to activate that line. Now, what does the preset and the clear lines do? Well, basically, if you provide a 0 to the clear line, the flip-flop will clear. It means it will have a 0. Now, you may be saying, hey, but that's like reset. Clear means it will flush it out. Whatever was there inside there, it will flush it out, right? And it will store the number 0 inside. But you will say, and Q will become 0, and Q bar will become 1. But you'll say, hey, hang on. When we used one of our lines in JK, I think J is 0 and k is 1, if you make 0 and j is 0 and k is 1, we can make our flip-flop to be reset as well. So clear and reset are the same things, except for one you are using just a one line, the clear line. You have to provide a clear, 0 to the clear. If you provide a 0 to the clear line, what happens at the bubble? The bubble converts it to a 1, right? So 1 goes inside. So you provide a 0, right? So the bubble indicates that you provide a 0. You provide a 0 to the clear line, and the flip-flop will then clear. It will store a 0. But you will be saying, hey, this is like repetition. If you provide, just check if this is correct. If you provide a 0 to the j and a 1 to the k, doesn't that make your q equal 0 as well? 0 to the j and 1 to the k. Is that correct? Does that reset? Yeah, that's reset, right? Q becomes 0, right? You'll be going, hey, but that's repetition. And let me tell you, so just keep that question in mind. Why did we do this? Now let's look at preset. Preset, if you provide a 0 to the preset, because there's a bubble there, the bubble indicates that only low, active low will activate that line. Active low, low means LOW, active low, a 0 volt will activate that line. So can you see preset also has a bubble. The bubble indicates that only active low indicates that line. Remember we did this when we were doing multiplexers and we were doing decoders. There was active low enabled, right? Okay, now preset, what it does is it makes the flip-flop store the number 1, q equals 1. But you'll be going, hey, this thing starts to look very familiar. If we make j equals 1 and k equals 0, the thing will do the same thing. Why do we need another 2 extra lines there? Why do we need another 2 extra lines over there? Well, the answer is, what if you end up with a circuit okay, let's look at this. What if you end up with a circuit like this? Right? Now, and you wanted to now suddenly, all of a sudden, you wanted to let's say flip-flop 2, flip-flop 3 and flip-flop 4. You wanted to do a sudden change such that in the middle of the operation some condition is met and you wanted to suddenly make all the flip-flops 0 or make all the flip-flops 1. How would you do that? Now it will be very hard if you've got your synchronous logic worked out because the next state is already worked out according to your design. So if you want to interrupt the word, remember that word, it's going to come next year a lot. If you want to interrupt the circuit and suddenly, like for example, the circuit continues according to the state diagram, right? Remember, you guys have done the project, so by now you're fully aware of how the state diagram works. So the state diagram goes in circles and all that sort of thing, fair enough. Now, all of a sudden, you want to interrupt the circuit and make it go down all to 0, or make it go all to 1, or maybe make one of the flip-flops 0, one of them 0, all of them 1. You can't do that from your thing because you've already designed it according to your state diagram. The next state will be what you have drawn in your state diagram and then the state table, and that's how you got all those, you know, all that big circuitry, the chunks of the AND OR circuitry which you guys did, like in your project. So how do we suddenly intervene in the middle and clear everything, make it all 0, right? Now the way you do it is by using the preset or the clear. If you want to make a particular flip-flop or all of them 1, use the preset, right? What do you provide to the preset? You're going to provide an active 0, active low. If you want to make all the flip-flop 0, you're going to use the clear line. What are you going to provide to the clear line? You're going to provide a 0, okay? So remember that. That's a very important point. Okay, now. So that's your preset and that's your clear. Is somebody's exam paper, eh? Okay, all right, multiple choice. Okay. All right, let's come here now. Now, let's have a look at this particular circuit here. Can you see in this particular circuit, we are using our clear line. We are using our clear line. So the moment a particular condition is met, and over here we were trying to develop, I think we were looking at it last week, they're trying to develop a mod 16 ripple counter, asynchronous counter, right? And you must know what is the word ripple, it coincides with the word asynchronous, right? It's mod 6 asynchronous counter. Mod 6 means it will count to the number 5, and after the number 5 it will return back to 0. Now the thing about asynchronous counters, what's the difference between asynchronous and synchronous? Well, obviously the first difference is how the clock is connected. Everyone knows that, right? Okay, the clock in synchronous is all tied together, so it's all synchronized. In asynchronous, it gathers its clock from the previous line. Okay, fair enough. All right, now, what happens in this particular scenario? What happens when another major difference is that asynchronous counters generally we only use them to count in proper sequence. In proper sequence, meaning 0, 1, 2, 3, 4, 5, 6. Doing random numbers is possible, but very, very complicated, right? Like if I gave you the problem in doing asynchronous, like your problem, by now you guys have mastered the synchronous problem because you did such a large project with all the different numbers, so many gates to draw, so many Kano maps. So you've done the project, this becomes really easy. Now, in synchronous, if you want to do random numbers, that's like what you did in your project. Straightforward system. In asynchronous or in ripple, very difficult, very, very difficult, right? For every scenario, you have to do a reset, or you have to do a preset, or you have to do a preset, or you have to do a clear. Okay, now, asynchronous counters, another name is ripple counters, they only go in proper sequence. So they go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you're using 2 flip-flops, what is the maximum count? The maximum count is 2 flip-flops. Maximum count will be 0 till 3, right? Because 2 flip-flops 0, 0 goes till 1, 1. If you're using 3 flip-flops, it will go from 0 to 7. 4 flip-flops from 0 to 15. 5 flip-flops 0 to 31. Fair enough? You guys get the picture now. Okay. Now, you can also do, you may be wondering, hey, what if I want to count only from 0 to 9 or 0 to 5? So what you're going to do is, the moment it reaches the number 5, so number 5, let's consider this example. The moment it reaches the number 5, you have the number 5 is 101. The next number is 110. So 110, the cues from the 110 must trigger some gate circuit to go and clear. Because from 101, it will reach 101. The next number is 110, and then it's going to do 101, which is the number 5. So it goes from 0, 1, 2, 3, 4, 5. After 5, it's got to return back to 0. How are you going to do that? After 5, you're going to return back to 0. So, what are we going to do? We're going to go to number 5, do the next count, the number 6. As soon as it reaches 6, 6 is what? 110. So flip-flop 1 will store 1, flip-flop 2 will store 1, flip-flop 3 will store 0, right? So the moment it hits 110, it then resets the circuit, right? It resets the circuit, right? By what? By using a NAND gate. If you want, you can use a sum of product system or product of sums, but that uses a lot of gates. If you just use one simple NAND gate, you can then activate the clear line by sending a active low. All right? Okay, you get what I'm saying now? Right? So the moment that particular combination is reached, the combination of having 1, 1, 0. All right? Okay. Yeah, 1, 1, 0. Flip-flop 3 and flip-flop 2 will have 1s. Flip-flop 1 will have 0. All right, let's have a look at the other circuit. Right? And this is the timing diagram. Now, have a look at this timing diagram, guys. This is the timing diagram. Now, compare this timing diagram. I want you to look at the first timing diagram. The first timing diagram, can you see everything? What happens in every flip-flop? It is dividing the frequency by 2, right? We did this frequency division. We did this in our last lecture. Now, let us now consider the next timing diagram. There we go. Okay, that's the next timing diagram. Can you see it counts from 0? How do we know the 0? It counts 0, 0, 0. Then it counts 1. 0, 0, 1. Can you see flip-flop 3 is the least significant. Flip-flop 2 is the middle one. Flip-flop 1 is the most significant. 0, 0, 1. Look at the second count, the second clock pulse. One clock pulse is one low and one high. Now, the third clock pulse, it's 0, 1, 0. Fourth clock pulse, what do you get? Right, I want you to focus on the lines, right? Fourth clock pulse, can you see number 4 on the clock written over there? You go downwards and you'll see 0, 1, 1. Now, the fifth clock pulse should count the number 4. Because remember, the first clock pulse was counting the number 0, 0, 0, 0. Now, the fifth clock pulse should count the number 4, which is 1, 0, 0. Sixth clock pulse is counting the number 5. Look at the clock. The number 5 is 1, 0, 1. Now, the seventh clock pulse, it will try to go to what? Naturally, those ripple counters, they go in sequence. The seventh clock pulse, it will try to go to the number 6, which is 110. It tries to go to 110. Can you see there's a small, those lowercase a and lowercase b. It does do a 110 for a very short microsecond. But because there's a gate over there, what does the gate do? It resets all the flip-flops and they all return back to 0. After returning back to 0, again, start to count 1, 2, 3. All right? So remember that these things here, synchronous counters or asynchronous counters or ripple counters, they count in sequence. Synchronous counters, they count according to your state diagram, according to the designer's state diagram, right? We can do random numbers here like your thing, but it will be very, very messy, very, very messy. And basically, the only tool you have is to use the preset and the clear. How many times are you going to use that? All right? Okay. Now, let's have a look at the next picture. Right. Okay. Guys, now, I want you to work out for me what is the scenario here. I give you a small exercise. We won't have a very long lecture. We'll finish very shortly. I want you to work out for me what is the scenario in this particular diagram. What number is it counting till? Remember mod, the word mod, the word mod means like if it's mod 12, so it counts till number 11, and then after that resets. Now I want you to work out, there are 4 JK flip-flops, and each of the JK flip-flops, what do you notice about J and K? They're always the number 1. And what mode is that in? That's in toggle mode. Toggle mode. What other flip-flop? What are the, can you please note this down in your exercise book? There's only 2 flip-flops which you can use to make ripple counters. The first one is you can use JK or you can use T. Right? Why? Because you can't have a toggling thing in SR. There's no toggle feature in SR and D. There is no toggle feature. Only toggle feature is where? Is in the only 2 flip-flops which can toggle are what? The JK flip-flop. And how do you make it flip-flop, JK flip-flop toggle? You provide J equals 1, K equals 1. That's why you see always J equals 1, K equals 1. Can you see there's nothing going into the gates? There's no gate system going into J and K. Like if you look at your project, now you're so familiar with your project. If you look at your project, J and K, the entry point was like filled with a big gate system and OR system. Over here, no more. Simple. Right? Okay. Now, what about thing? What about your T? How can you make your T flip-flop toggle? Can you see your excitation table? What can you do to make it toggle? Your input has to be 1, right? If you make input 1, it will toggle. If you make input 0, what happens? It's in memory mode, yeah? Is that correct? Okay, T is only 1 input. So again, you're just using a 1. Now, what is happening over here? It's a ripple counter, I can tell you that. It's a ripple counter, right? Now, it will count all the way till what? It will count until, can you see, let's go back to the clear line. That gives us an indication. Now, maybe I break down the question. I ask you this simple thing. When does the clear line activate? When does the clear line activate? Try and work that out. Follow the clear line. When does the clear line activate? Okay, let's see. The clear line comes from the NAND gate, right? What's the input into the NAND gate? It's D and B. D is where? D is flip-flop 4 and B is flip-flop 2. Now, in order for the clear line to activate, it's going to have 0, right? So, D will be 1 and B will be 1. So, if D and B are both 1, 1, 0, 1, 0, thereby what will happen? The clear line will become 0, the output from the NAND gate will be 0, the clear line becomes 0, which means everything, all the clears are fixed together. So, 1, 0, 1, 0. So, 1, 0, 1, 0 is what number? The number 10, right? So, this thing counts from 0 till 9, because at the number 10, the clear line activates, right? Okay? All right, so it comes from 0 to 9. What we worked out, the clear line will activate on the number after the maximum, on the number after the maximum, okay? It activates on the number after the maximum. So, it will count till the number 9. The next iteration is the number 10. Number 9 is 1001. Number 10 is 1010, 1010, right? Okay? So remember, 1010, when you look at the flip-flop, it's actually the other way around. Flip-flop 4 is storing 1, flip-flop 4 is the most significant bit, flip-flop 3 is middle, flip-flop 2 is middle, flip-flop 1 is least significant bit. So if you look at it from that point of view, 1010, right? You can rearrange your flip-flop, like some people in our projects, they arrange their flip-flops vertically. That's okay. Some people, they even arrange their flip-flops in a square, 1, 2, 3, 4, right? And they put their LEDs on top. That's all right. Still works. So long as the diagram, the wiring is correct, it'll work. Okay? So just the rearrangement of this flip-flop. The most significant flip-flop is flip-flop 4. Remember how when we did our state table, we said Q3, Q2, Q1, Q0. Flip-flop 4 is the most significant. Flip-flop 1 is the least significant. All right? So 1, 0, 1, 0. The two places where there's ones, that goes into our NAND gate. NAND gate output becomes 0. Bang. That follow there becomes thing. Is there any other scenario where you can have, if you go for a 4-bit system, is there any other scenario where flip-flop 4 and flip-flop 2 can both have ones? Can you think of it? Somebody might say, hey, 1, 0, 1, 1. How about 1, 0, 1, 1? But by that time, 1, 0, 1, 1, it's already, before even reaching 1, 0, 1, 1, right? It's already been reset. It's already gone back to 0. So it never reaches 1, 0, 1, 1. What's another number? 1, 1, 1, 1 or 1, 1, 1, 0. No, 1, 0, 1, 0. Yeah, 1, 1, 1, 0. By the time, even before, it never reaches 1, 1, 1, 0. So we were able to get out of it very easily using a simple NAND gate, right? You have to be careful. Sometimes just a simple NAND gate won't work. A simple NAND gate won't work, all right? You have to be careful, right? Depending on the scenario. If it so happens, you see over here, we only use 2 of the inputs, right? Some people would use sum of products. Let me give you a chance to discuss. How would you do, let's say the maximum count was 9, 1, 0, 0, 1. After 1, 0, 0, 1, it's going to reset back to 0. It's going to clear back to 0. So if you used to use sum of products, what would you do? So for 1, 0, 1, 0, it'll be Q and Q4 and Q3 bar and Q2 and Q1 bar. But can you see that's a very large gate circuit. You can just do a simple NAND to get away with it. All right? That's the point I'm trying to make over here. You can sometimes do a NAND, sometimes you might need a larger circuit. Because the larger your thing is, the slower your counter becomes. The larger your gate system over here is, the slower your counter becomes. This is a chip of a counter. Clear thing. Okay, let's have a look at this. This is, what is this? What can you tell me this does? What's different over here, guys? Can you make an observation? What's different in this particular scenario as compared to the other 2 circuits which we were looking at last week? This is a new type, same circuit. It's still a ripple counter. I'll give you that. It's still a ripple counter. We're still using JK flip-flop. I'll give you that as well. Right? It's 3-bit system, 3-bit. So what is different? Just tell me the observation. Observe and tell me what is different here. Sorry? Yeah. Go on. Say it. Huh? The next state is, okay. Anyone? Can you see, what can you tell me about the clock line? Clock line is driven by Q bar. Clock line is being driven by Q bar. Therefore, this becomes a down counter. Becomes a down counter. All right? It becomes a down counter. Q bar. All right? It becomes a down counter. So the largest number possible is 111. It goes down all the way to 0 and automatic reset back to 111. Okay. So the only thing you need to do is, if you want to, but hey, I want to point out over here. Your outputs are still being drawn from your Q. Your Q is your output. So your LEDs, you'll connect it to your Q. Now you've done your project, things become much easier for me to explain. Your LEDs will connect to your Q still, just like how you did in your project. But can you see your clock line is now coming from Q bar. Clock line is coming from Q bar. There we go. 2 necessary changes to convert. Right? So can you see they changed this line here. All right. Okay. All right. Now, guys, I would like you to, that's it for asynchronous counters. That's it for asynchronous counters. I just want to show you something over here. That's clock. Now, remember in our previous lecture, we talked about what is a trailing edge and what is a leading edge. Please take note of that. What is a trailing edge? What is a leading edge? What is a falling edge? All right. What is a rising edge, falling edge? These are same names. High to low, low to high transition. What is the preset? What is the clear? These are the two of the same things. Now, this is the behavioral table. Now, I want to make a point over here, guys. Is it possible that clear and preset, is it possible from our earlier explanation? From our earlier explanation, is it possible for clear and preset both to be 0? No, you can't use that. You can either make the flip-flop 1 or you can make it 0. Preset makes the flip-flop 1, right? Remember, I think most of you guys were using Logisim. 1 or 2 people use Circuit Maker, right? For Circuit Maker, they use the preset and the clear. For Logisim, when I said, hey, I want to look at the, when I came to mark you, I said, hey, I want to look at the the unused state. Or the tutor said, I want to see the unused state, 1, 0, 1, 0. So you went and click on the flip-flop itself. What you're actually doing is you're using the preset and the clear line in a software version of it. All right? Okay, so that's what you're doing in hardware. If you get to build it in hardware, that's what you'll have to do. Okay, so you have your preset, you have your clear, right? Okay, and you can't use both. You can either make your flip-flop 0 or you can make it 1. If both of them try to make it 0, they'll start to fight, right? There'll be an internal battle in the system, and both of them will try and, preset will try to make the flip-flop store the number 1, clear will try to store the number 0, right? So we don't use both. That is an unused combination, right? Okay, so this is the truth table. Okay, and if it's both are 1, yeah, that's okay. If both are 1, that line becomes unaffected. If both are 1, that's all right. That line becomes unaffected. Those lines only activate with the logic 0, the preset and the clear lines. Right? Okay? All right, guys. That's it for today's lecture, and please prepare yourself for the short test. This, by the way, is what it looks like inside, how the preset and the clear lines are done. Right? Same thing. It's like an SR flip-flop. And this is how, basically the second set of flip-flops, you then insert a clear and a preset line. But it's always got to be a 0 line, right? Because the 0 input going into a flip-flop results in a, going into an NAND gate results in a 1. All right, any questions, guys? Any questions before we knock off for your test? Any questions? Right, today's lecture will be examinable in the test, okay? All right, and this is the end of the syllabus now. So on Thursday, what we will do is I just want to show you, I want to share with you some real life circuitry, how to build a stopwatch, how the traffic lights are done, and all that, okay? But now you have the knowledge of how to build it. Okay, thank you. We'll see you on Wednesday for the lectures, and then Thursday we will discuss the format of the paper and all that sort of thing.